Okay, so um, I'm writing for the first time on a table here, and I'm trying to, instead of standing in front of a board, I'm just going to turn my laptop down, and uh, and hopefully this will work. Um, let's be writing on these notes. So this class is really two classes, right? So it's hydrogeology is the title, but it's cross-listed between Environmental Studies 301 and Geology 320. So there are geology majors in this class and environmental studies majors in this class, and in some cases, people who are majoring in both. Uh, so people are coming at this with different backgrounds, which is one of the really fun things about teaching this class is there are people who have a real interest in geology and in connecting water and geology, and other people who have a broader interest in the environment, and obviously water is a huge and important part of that. So given that we have different backgrounds, what I do on the first day, and that's right now, is I cover a little bit of the kind of basic geology that you would get in an introductory class. So for geology majors, you've seen this before, and for those of you who've had intro geology, you've seen it before. We're not going to do anything in any detail, but some of you may not have seen this, and so it's worth covering. Also, even if you have seen it once, it doesn't hurt to get a refresher. So, so when we think about hydrogeology, basically there are two areas that we're primarily concerned with, and those are surface water and groundwater. And groundwater, as we will discuss in more detail later, really is what's so important. It's where the vast majority of potable, drinkable, fresh water is stored. It doesn't suffer from evaporation. It doesn't move very fast. And it's pretty much everywhere. The driest parts of the world you can imagine, if you drill down deep enough, you most likely will find substantial amounts of water. Whether or not it's salty or good tasting is another question. But there's water just about everywhere. And so that water that's in the ground obviously is stored in the rocks, and hydrologists and geologists often work together because if you know what kind of rocks are there, you can make some pretty good educated guesses about where the water will be, how fast it can move, whether it's susceptible to pollution from the surface, and so forth. So anyway, with all that in mind, we're just going to talk a little bit about those rocks. So what you all probably know is that there are three fundamental types of rocks, and those are sedimentary and igneous and metamorphic. Now, in most parts of the world, sedimentary rocks are by far the most common at the Earth's surface, and that's because they're formed at the Earth's surface. So sedimentary rocks are generally formed, not always, but a lot of them are formed below sea level. And so that's what that's supposed to represent. There's the ocean and there's a tree by the ocean, so you can see which way is up. And when rivers bring sediment through rivers, when rivers bring sediment down to the oceans, which they're constantly doing, nature is constantly wearing away the earth, the portion of the earth that's up above sea level, washing it downhill due to gravity, and depositing those ground up pieces of rock on the ocean floor. And so we have these layers of sediment that are slowly building up over time at the bottom of the ocean. Now, you might think, well, why doesn't the ocean fill in over time? And that's a longer discussion, which we'll get to in a minute. But the broad answer is that the oceans are constantly being created and destroyed, and the sediment that fills those basins is constantly being scraped off or recycled as well. So anyway, those are sedimentary rocks. So sedimentary rocks are rocks that are generally deposited in layers, and those layers are called beds. Strata is sort of a more generic term for the more or less horizontal layers of rock that are deposited. And they're, again, deposited by rivers that wash sediment into the oceans. That's what happens along the continental margins. When you go further out into the oceans, you get something very different because no rivers are strong enough to wash sediment 50 or 500 miles out into the middle of the Pacific. So the sediment that piles up, and it generally piles up much more slowly at the bottom of the ocean, is a product of all of the little critters that are living in the water column, dying and slowly settling out. So these are dead whales, dead fish, but mostly the trillions and trillions of plankton that are floating around in their little shells, so forth, and they die and sink to the bottom of the ocean. Igneous rocks are rocks that are formed from a melt, meaning they were at one point so hot that they were liquid. This is generally 700 to 1100 degrees Celsius, so double that, maybe 1200 to 1500 degrees, 2000 degrees Fahrenheit, something like that. Very, very hot. And they form in association, of course, with volcanoes, but there are lots of places on Earth where you get molten rock without the rock actually ever coming up to the surface. Why that rock melts, again, we're going to get to in just a second. And then finally, metamorphic rock. Metamorphic rocks are rocks that are altered by intense changes in pressure and or temperature. So they get squeezed and they get heated generally, but not so much that they melt. Those intense squeezings are often, but again, not always, often associated with the formation of mountains. So when two tectonic plates crash together, you get huge areas where the rocks are being squeezed and shoved down into the earth and heated. And in places like that, like along the Himalayas, for example, you get these rocks get twisted around and reshaped into these things called metamorphic rocks. Okay, so that's that. So I've got to get used to this, so I've got to look at my clock. So that's about, we've still got some time. All right, so the next thing to talk about is sort of the grand theory for geology, and that's this thing called plate tectonics. Oh, before I forget, I'm going to post some and talk over some images of sedimentary, igneous, and metamorphic rocks in a minute. It's just a pain to go back and forth between the two. So what I'll do is I'll kind of lay out the lectures like this now. Then I'll post another video where I'm just talking over some images to help show you what they look like, so forth. All right, so plate tectonics, as I said, is this idea that is, by and large, explains pretty much everything we need to know about the big picture of the way the Earth works. And what this basically means is that the Earth itself, which I'll draw here, is divided up into a whole series of interlocking pieces. And those interlocking pieces, which don't look anything like this, but I'm just using it as an example, are called plates. And the plates can move towards each other, or they can move away from each other, or they can move past each other, depending on what their relative motions are. And it's those moving together, moving apart, or moving by each other of the tectonic plates that causes earthquakes, it causes volcanoes, it causes the uplift of mountains, it causes the creation or destruction of oceans, and in the case of places like Iowa, it's the reason that we have absolutely nothing going on here geologically. It's why there are no mountains, why it's boring and flat, and so forth. So we're going to take a break here in a minute, and when I come back, I'll sort of dig into the details of plate tectonics, which will explain to you, as I said, sort of why we have the rocks that we have.